My name is Emily McInturf, and this is my lab report on the motion of a falling object. The objective of this lab was to observe the motion of an object that is dropped from rest and falls somewhat slowly, and then understand how it works through the application of Newton's second law. In order to show this, I recorded my friend dropping a dry erase board eraser. The motion was analyzed using Tracker and then modeled through vIDLE. I then compared the position as a function of time in the measured experimental case and the predicted model case. The main principle applicable to this lab is Newton's second law, which can be written as Vf equals Vi plus F net over m times delta t. When an object is dropped, we must account for the two main forces acting on the object: weight force, or the force of gravity on the object, and drag force, or air resistance. This is the video in Tracker. The eraser is the system and everything else is the surroundings. As you can see, the eraser moves down the negative y-axis. I used Tracker to obtain the y position of the eraser as a function of time. This is the data found in Tracker. The time goes from 0 to 6.33 seconds, and the position goes from 0 to negative 1.644 meters. The object is dropped from an initial velocity of 0 meters per second and has a final velocity of 3.75 meters per second. After analyzing the video in Tracker, I plugged the observed data into the code provided to make a computational model in vIDLE. I first entered the mass of the eraser, the initial position, and the initial velocity. Next, I chose a time step of 0.001 so that we could have multiple points and more accurate results. We then state that g, the magnitude of the gravitational field near the Earth's surface, is a constant 9.8 meters per second squared. Finally, through trial and error, I set b, the drag force constant, equal to 0.0025 to simulate a drag force close to the force present in the system. Next, we use a while loop that iterates until the end of the video, which is 6 seconds. We use the Newton's second law of motion equation to predict the new velocity at each time step, and then this position equation to predict the new position. The most important part of this while loop is calculating the net force. Because the object is falling, we say that F net equals the weight force plus the drag force, where weight force equals mass times J hat times G, and the drag force equals drag constant times velocity. When we run this code, we get a computational model of the position versus time graph and also a model of the forces on the object. The yellow arrow represents the gravitational force from the Earth, and the blue arrow represents the drag force. This is a graph comparing the position as a function of time for the computational model and the experimental data found in Tracker. The model is in red and the experiment is in blue. As you can see, both graphs start slow and then begin to slope further as time goes on. This is because the bottle starts from rest and is gaining momentum, causing it to speed up as it gets closer to the ground. The graphs are approximately similar, however the model falls farther in the end. This may be due to the drag force constant I set in the model. If I set b too low, the model assumes there is less drag force and the object will fall farther. What does it mean? The model with drag will reach a terminal velocity because eventually the drag force and the gravitational force will equal each other, making the net force 0. And by Newton's second law, we know that if the net force is 0, we have a constant velocity. What if? An object reaches terminal velocity when the weight and air resistance are the same. An object has the same weight regardless of if it's thrown or dropped. Therefore, the terminal velocity would be the same in both cases. This concludes my lab video. Thank you for watching.